Okay, so now we go on to trees. And the cool thing about trees then, I'll just tell you the whole thing first. It's like the Holy Grail. It's the Holy Grail of data structures. Because where arrays have the disadvantage of being static, you define an array as taking up 10 times 32 bits, and it takes up 10 times 32 bits, or a million times 32 bits, and you're wasting all of them until all of them are full. So it's static and it has that problem. What you can do is a binary search. If I'm looking for a number in a sorted array, blah, 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 blah. Well, I keep on doing this, 200. All right, you can do the binary search, right? I'm looking for number 7. Is number 7 here? No. If number 7 is not there, then I can eliminate that other half of the array, right? And then I look for the middle one here. Is it 7? And I lucked out, right? So you can do a binary search with an array. It's static, can't grow it, can't shrink it, but you can do a binary search. So then you've got your linked list. Your linked list is not static. It can grow, and it does not waste memory, because each node points to the next. And if you want to delete one of them, you can do so from the end or from the middle or whatever. So they are dynamic. But what they are not is binarily searchable, because when you're searching through a linked list, it's sequential. 1, 2, 3, you're looking through it. So if you have, worst case scenario, an element that you're looking for in the last element of, say, a million element linked list, then it's going to take you a million steps to get to it. And that's pretty bad. So the tree comes to the rescue, because the tree, if I take the main advantage here, main advantage of an array is that it is binary searchable. I'm not going to write it because it's binary searchable. The main advantage of a linked list is it is dynamic. The tree has both. The tree is both dynamic and binary searchable. So here it is. I think probably you understood that to this point. Here's how the tree works. Each node has 3 parts. It has the data, and it has 2 pointers. And as you can imagine, the left pointer points to a left node or leaf, and the right pointer points to a right node or leaf or child, however you want to put it. And let me see if I can copy and paste some of this. So it grows and grows and grows, and I can't go much further than that, as you can see, but you can see how the structure is forming. Like a tree, it grows like a tree. And maybe I'll just put a couple more branches. Go like that, maybe. The trees are not always perfectly symmetrical. And there are better diagrams, obviously, on my website, but this will give you an idea. And so this can grow. We're going to have, let's say this is letters. And this is letter K. And letter E was added. I'll just construct this the way that it would be fine. That's going to have to be N. I'm putting these in the wrong place. Okay, so if you take a look at this, this is made, what's this supposed to be, f? This is made so that the nodes are attached to the right if they're greater than the root, and left if they are less than the root. So I added r to the k because r is to the right of k, or greater than k. I added an n to the left of r because if I add n, let's just do that. Let's add m. And we'll add a couple more. If I were adding m, so I want to add m, I ask, is m greater than or less than k? Greater than. Greater than or less than r? Less than. Greater than or less than n? mn. Less than is greater than or less than l? lmn. So it goes over here. M. What if I were adding c? Left or right? Okay, left or right? Left or right? So I would add it here. And C would get added there. And we'll just add one more. S. Right or left? Right or left? Right or left? And S would go there. So here's the beauty. Well, you're seeing live one part of the beauty. One part of the beauty is it is dynamic, right? You're not wasting any more memory than is needed. We need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times whatever a node takes in memory. That's it. And we can keep on adding infinitely. Right now this takes 11 times, let's say, 16 plus 2 pointers, 32, 32, 64, 76. So 76 times 11, 700, and let's say around 800 bytes. But we keep on adding this. This could have 1 million or 2 million, whatever it would take. So dynamic. So trees are, number one, dynamic. But they're also, number two, this is the part you haven't seen yet, binarily searchable. Binarily searchable is what that says. They're binarily searchable because what if I want to go looking for S? I say, okay, where is S? If S is any place, is it over here? Answer, no. Is it over here if it's any place? Yes. If it's any place here at all, it's got to be here. So I'm eliminating, when I'm looking for S, the very first step, I'm eliminating all of that just in a binary way. And then I'm looking over here. Is S greater than or less than R? RS. It's greater than. So I will have eliminated half of the remaining, theoretically, right? And so on and so on and so on. So I can locate it by eliminating half. Greater than, greater than. Greater than, less than, greater than. Greater than, less than, less than. So in 1, 2, 3 steps, I have found it. And you could picture in your mind's eye 1 million of these in a perfectly balanced binary search tree. The maximum number of levels we could go is 20. Log 2 of 1 million. So it is both, as you can see, dynamic, and as you can see, binarily searchable. Trees are the best data structure, both in terms of memory and in terms of speed. I won't write that because okay, they're dynamic, so they reserve memory, and they are binary searchable, so they are fast to search. They want you to define the terms parent, left child, right child, subtree, root, and leaf. Okay. What is the parent of n? Good. Left child, what is, what is the left child of E? B. What is the subtree of, that would be a good one for this. What is the subtree of N? It is, right, it's like, it's that. It's L and M. And so some subtrees could be huge, right? But the subtree. And the root, which is the root? Okay. And a leaf, a node which does not have a child. Yeah. So how many leaves does E have? The answer is 0. Or no, 1. That's what you said. 1. Yeah. Does any of them have 2? Like, this is L, A. I think. Well, assuming that is correct, L has 2 leaves. T has 1 leaf. Okay. So that's that. Here it gets, looking at the clock, here it gets a little bit harder to fully understand. But the thing is, you need a way to go through all of these. To go through an array is easy, sequentially. Get that, print it out, get that, print it out, get that, print it out. Same thing here, get that, print it out, get that, print it out, get that, print it out. It's a little bit harder to imagine how we're going to get all of the values printed out on one page of a tree. So if you take a look up here, there are different ways you can do it. You could go to here, back to here, to here, back to here, to here, 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 or you could go there, 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 there. So there are different approaches to traversing, is the term, traversing through the entire tree. And they want you to know generally 3 of them. And again, it gets schmancy, but to show you how schmancy it gets, let me show you one of my favorite former huge jobs. This is a binary search pre-order traversal. And the pre-order, and that's the cool part, echoing back to what we've done actually this afternoon. What is this an example of? There's your pre-order method. This is a method. Okay, this is a function. So what do you know about this pre-order function? What kind of a function is it? Is it an iterative function? Or is it begins with R?
It's recursive.
It is. It's a recursive function. Because in the middle of doing pre-order for a particular value, it does 2 other calls to pre-order, one to the left and one to the right. I'll put this in overdrive first of all, and you'll see how it traverses. Okay, I'll do a little bit fast. And if you really want to understand how recursion works, you slow this down, take it one step at a time, and you'll see. But what you really should be focusing on is just the way in which it's able to visit every single node. And here's a perfect answer to the earlier question. Why would you ever use recursion? Because sometimes with very, very few instructions, you can accomplish an incredible amount. So you can imagine traversing through a tree of 1,000,000 nodes. How many lines do you need? 4. Now, you're going to end up calling 500,000 other instances of that pre-order, but that pre-order itself, A, it's only 4 lines, and B, it makes sense that what we're going to do is we're going to add, over here we're adding to the string, if I just go through it slowly. Right, I just want to add the 10, 15 to 10. It's still going too fast. And what is it doing each time? It's visiting the left and visiting the right after it's added the string. It's added the string 60, so now it's going to visit left. But it gets interrupted. Blah, 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 blah. So that's something you don't need to understand in the present curriculum. But you should know. Again, this is more for exam preparation, stuff you're going to do next year rather than it is for the dossier. But you know what I mean, if somebody got really ambitious, they could implement a tree. They could get tree code, and they could, you know, have their data of their dossier treated as a tree, and then they would have to choose how do they want to traverse it: pre-order, in order, or post-order. And the answer to that depends on, do you want to see the numbers in order, alphabetical? Do you want to see them reverse alphabetical, or do you want to see them neither? And let's just see what the videos are here, so I don't think I need to go any further, particularly given the time. But let's just jump in on one of them. Jump in on the same one that we were just looking at. Pre-order traversal of a binary search tree. We start at the root, and we'll watch 30 seconds of it then. Does itself first. So let's print it out. We'll go F. The second thing that this instance does is it looks to its left child, which is B. And so B, pre-order, comes into memory, and the F1 gets put onto the unfinished stack, so we're dealing with B now. So where does B start? B starts at the beginning, and the beginning is root, so it does itself. What does it do next? It looks at its left child. Its left child is A. So now A is at the top of the stack. A is being dealt with. So A starts. A starts at the root. What does it do? It prints out itself. Then it goes to its left, which is null. So it's just finished. Goes to its right, null. So A is now finished. A is the first in this bunch to have finished because it has done itself, it has done its left, it has done its right, it is finished, it is out of memory. We come back to B. B was interrupted when it did its left, so it's finished doing the first two lines. Now it goes to the third line. It looks to its right. Its right is D. So D now comes into focus. D starts with doing itself first. So D. And sketch binary trees. Good exam question, pretty easy. I've got a video showing it, and that's basically what I did over in Photoshop. I was just adding stuff on. And there are pictures removing each of these, and there's a video that goes with it. So, again, this is not really something that's one of your top things for your dossier, but you could. Just notice that there is no tree class that we've been using. We've used array list and link list. We haven't had a tree one. You have to make it on your own. But you go to My Java Revolution, do that if you wanted. And that's it for trees. So I'll stop this and we'll do the last three as a separate video.